Today's lesson is section 10.1, sequences as functions. In this section, we're going to learn about two different types of sequences, arithmetic and geometric. First, let's talk about some terminology. A sequence is a set of numbers in a particular order or pattern, and numbers in a sequence are usually separated with commas. We can call each number in the sequence a term. If a sequence is finite, that means it has an end. If a sequence is infinite, it continues forever and ever, and you can see that it will be denoted with 3 dots. One type of sequence is an arithmetic sequence, and you know that a sequence is arithmetic if it has a common difference. That means that the difference between each subsequent term is the same. Let's take a look at a few examples. 4, 8, 12, and 16. We can call this an arithmetic sequence because it has a common difference. An easy way to find that common difference is to think about traveling from one term to the next. To get from 4 to 8, you add 4. And to get from 8 to 12, you add 4. And to get from 12 to 16, you add 4. So since we are doing the same operation each time and it's an addition, we would say that that common difference is 4. Here's another example. We have 10, 4, -2, and -8. And again, we can think about from one term to the next what's happening. Well, in this case, it's -6, -6, and -6. This is an arithmetic sequence because we have a common difference of -6. In this example, we want to determine whether each sequence is arithmetic. And remember, in order for a sequence to be arithmetic, it must have a common difference. Between -3 and -8, that common difference is -5. And between -8 and -13, that's also -5. But to go from -13 to -23, it would be -10. So because these are not all the same, we would say that it is not an arithmetic sequence. For the next example, to go from 8 to -2, you subtract 6. And to go from -2 to 4, actually, let me think about that for a second. My screen, okay. My view, I couldn't see that negative in front of the 8, but it actually is a negative. Okay, -8 to -2, sorry, that is +6, and -2 to 4 is +6, and 4 to 10 is +6. So since these are all the same, our common difference is 6. And yes, this would be considered an arithmetic sequence. In this example, there's definitely a pattern going on, but again, to think about whether or not it's arithmetic, we want to think about the difference between each term. To go from 1 to 2, you add 1, and from 2 to 4, you would add 3, so we can see right away that this is not an arithmetic sequence. Find the next 4 terms in each arithmetic sequence. We have -8, -6, -4. So here the pattern, we're adding 2 to each term. The next 4 would be -2, 0, 2, and 4. In this pattern, we have 9, 2, and -5. So the pattern here is we're subtracting 7 each time. To find the next 4 terms, you can continue to subtract 7 over and over, and you should get -12, -19, -26, and -33. There's another type of sequence that we're going to look at called geometric sequences. A geometric sequence has a common ratio. So instead of adding or subtracting a constant to each term, now we're going to be multiplying by a common ratio between each term. In this first example, 81 and 27 and 9, the common ratio is 1/3. A really easy way to figure out those common ratios is to take subsequent terms and divide them. You can take R2 over R1. Oh, I'm sorry, I should call this A2 over A1. So this would be like the second term over the first term. So in this case, it would be 27 over 81. And if we simplify that, we get 1/3. We could also take A3 over A2, so the third term over the second term, in this case 9 over 27. If we simplify that, we get 1/3 again. It's an easy way to check that you actually have a common ratio. And in the next example, 1, 2, 4, and 8, between each term, to get from 1 to 2, you're multiplying by 2. From 2 to 4, you're multiplying by 2, and from 4 to 8, you're multiplying by 2. Since it's a constant multiple, or a common ratio, we know that this is a geometric sequence. In this example, we want to figure out whether each sequence is geometric. We have 64, 16, 4, and 1. Well, we can use that idea of subsequent terms. Is 16 over 64 equal to 4 over 16? And is that equal to 1/4? If we simplify each one of those, they all equal 1/4. So yes, this is geometric. In the second example, we can try the same method. Is 30 over 19 equal to 41 over 30? Is that equal to 52 over 41? And if you simplify each one of those fractions, I don't think you actually can simplify any of them. And so they clearly are not equivalent fractions. So we can say no, that the sequence is not geometric. And for the last example, we have 8, 20, 50, and 125. If we try to do 20 over 8 and simplify, we would simplify and get, if we cut each one in half, or divide each one by 4, we would get 5 over 2. And then if we do 50 over 20, that is also equal to 5 over 2. And 125 over 50, that's also equal to 5 over 2. So yes, this is geometric, and the common ratio is 5/2. Find the next 4 terms in the geometric sequence. Well, first, let's think about what the common ratio would be. To get from 250 to 50 or from 50 to 10, here the common ratio is 1/5. So we can continue the pattern by multiplying 10 by 1/5, and we get 2, and then multiply that by 1/5, and you get 2/5. Multiply that by 1/5, and you get 2 over 25. Multiply that by 1/5, and you get 2 over 125. You can either leave them as fractions or convert them to decimals. Either way is fine. Now we're going to have a variety of different types of sequences, and it's our job to figure out whether they're arithmetic, geometric, or neither. In this first example, I can think about what happens to get from 13 to 25. Well, I'm going to try to start with arithmetic and see if it works. From 13 to 25, we can add 12. And to get from 25 to 37, we can add 12. And to get from 37 to 49, we add 12. Because we have this constant difference, we can say that this sequence is arithmetic. In this pattern, if I start by thinking the same way, to get from 2 to 5, we would add 3, but from 5 to 9, we would add 4. So we know it's not arithmetic. Well, is it geometric? Is 5 over 2 equal to 9 over 5? That common ratio doesn't work either. So in this case, it's neither. And let's think about the last example. So to get from 6 to negative 12, by adding and subtracting, the common difference method isn't going to work, but we could multiply. To get from 6 to negative 12, we can multiply by negative 2. And to get from negative 12 to 24, we can multiply by negative 2. And from 24 to negative 48, we can also multiply by negative 2. So we have a constant ratio here. It's geometric. One more topic that comes up in this section is the idea of a factorial. And the exclamation mark in mathematics refers to this factorial notation. A factorial is the product of descending natural numbers to 1. So the easiest way to think about a factorial is through example. The number 4 factorial is equal to 4 times 3 times 2 times 1. And you can simplify that. 4 times 3 is 12, times 2 is 24, times 1 is 24. This is a special case, 0 factorial equals 1. That's one of those special cases that you should memorize. It's the same idea as something raised to the 0 power equals 1 as well. So simplifying 7 factorial, we can do 7 times 6 times 5 times 4 times 3 times 2 times 1, and you can type that in your calculator to simplify. I'm going to skip this one. One more thing that comes up with factorials is sometimes you'll want to simplify 8 factorial over 6 factorial. There's a really easy way to simplify this. You can do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 6 times 5 times 4 times 3 times 2. So instead of multiplying these out and getting these huge numbers, remember with fractions, you can always cancel common factors. So the 6s, the 5s, the 4s, 3, all of those cancel. And it's all it is 8 times 7, which is 56. That's going to be it for our lesson today, everybody. Thanks for watching.